Thank you, Stefan, for the kind introduction. And hello, everyone. I'm Francesco. I'm here today in place of Shinan, the student that led this work, but who sadly could not be here to present due to visa constraints. And today I'll talk to you about the work that we have done in trying to help network operators make a better use of the machine learning models that they want to deploy into their networks. So machine learning models are being deployed every day into operational networks. They are particularly good for solving tasks across network management, in particular for problems such as anomaly detection, performance inference, and more broadly, forecasting of resources usage and demand. And machine learning models are particularly good in capturing the inherent relationships that there exist between the data that we can collect from our networks and the events that we want to track. Yet, a lot of attention has been given over the years to how to train highly accurate models that are very capable at the moment we have trained them. But we have given less attention to what happens to these models once we want to actually deploy them into the networks that we operate. So let's look at this from the perspective of an example. And let's say that an operator wants to forecast the demand that will occur in its network, and particularly on the base stations of its network, in order to take decisions about how to orchestrate its infrastructure. So in the first step, the operator will collect some data coming from its network, and he will use this data to train a model, his forecasting model. Once the model is ready, the operator will start predicting the demand for the upcoming future. And if it did a good enough work, the actual predictions will resemble to the events occurring in the network. Over time, the operator will continue using his model to predict. But let's say that at some point in this future, the operator strikes a deal with a service operator, a sort of deal that encourages the users of the network to actually demand a lot more resources. In that case, the actual demand occurring will diverge significantly from the prediction, causing a large error in this prediction. So the reasons of why this performance degradation can occur are varied and of different nature. We have changes that occur to the data that are periodic, like normal daily or weekly patterns in the traffic that we all know very well, or even like factors that are outside of the traffic, like seasonality. Foliage can impact a lot how cellular networks operate. Or we can also observe more sudden and drastic changes to the conditions of the network that can impact the prediction. And these factors can span from the installation of new equipment and base stations, a software upgrade that occurs on them, or more drastic events such as the deployment of a new generation. And well, the pandemic clearly was pretty disruptive in these changes. So we call this phenomenon of changing performance over time concept drift, and in particular, concept drift concerns the changes on the distributions of the data that is used by the models, or the changes in the relationship between this data and the outputs that we want to track. So while concept drift is a concept that is well studied across machine learning, this is actually less so for cellular networks data, and this is where our work comes into play. So the first question that we ask ourselves is, can we characterize how concept drift impacts and looks like in general on cellular networks? We did so by studying a 4 years long data set collected from a US metropolitan area in between the 1st of January in 2018 all the way to March 2022. This dataset was constituted of daily logs collected from all the base stations in the network, and included around 224 KPIs, key performance indicators, spanning from different categories, including resource utilization, like volumes of data created or number of users connected to the network, network performance, like throughput, and so on, or user experience, call drops, whether RTP services are performing correctly or not. All these logs were collected from all the base stations present in the network. And obviously, due to the length of this data set, the number of eNode Bs changed over time. We had about 400 base stations that were present throughout the deployment, the collection time, but a lot more base stations were either coming or going, depending on the evolution of the network. So we use this data set to study a common task that operators might want to perform, which is the prediction of network capacity demands 180 days in the future. Our task is to create a single model from all the input features that we're collecting from in the past from the base stations to predict the demand for all the base stations. We choose specifically 180 days because after discussions with the operators we were working with, we realized that forecasting, if done at too small of a scale, is not very effective because it does not leave enough time for the operators to actually take action into their network. And failing taking actions can cost them millions of dollars. So our approach was to train a large number of models across different families, different parameters, including how many days of historical data will be used to train these models, and try to predict, create different models to try to predict different KPIs. We selected 6 KPIs across 3 categories. In particular, to the explorative nature of this work, we use AutoML tools, in particular AutoGluon, to train a large set of models and study concept drift. And finally, we use an error metric to evaluate how well these models that we were creating were performing. In particular, we use normalized root mean squared error. Normalize simply because all these KPIs have very different values and ranges of possible values, so we wanted to have a way to compare across them. So what did we learn? As a first example of what we learned, I'm showing here the predictions, or better, the errors on the predictions of a specific model, a CATBoost model in this case. I forgot to say that all these models are regression models because we have to predict continuous values. And I'm showing the time series of the errors that we're obtaining, the MSE over time. And in particular, this model was trained for a specific KPI target, downlink volume, using 90 days of training data. So what we observe is that obviously there are inherent fluctuations on the performance of the model, which recollect to the periodic changes that we were discussing about before. But we also observe that there are 2 more ample spikes of errors centered around 2020, the beginning of 2020, colliding with the COVID pandemic, in particular the lockdown that forced us all into our houses, and a second spike arriving towards the beginning of 2021, when things were starting to go back to normal. Something that we observed, this is specific to the CATBoost model, but something that we observed is that these characteristics actually were shared among all the models that we were training. While some models were performing better or worse, in particular, we were surprised to see that LSTMs were performing the worst. In general, we observe the same trends over time. And while I don't have the time to show you all the details of this characterization study that we performed, we actually concluded that concept drift was a universal phenomenon, regardless of which models we will be using, like in the example I've shown you before, the training set size, so the amount of data that we were using to train these models, and the target KPIs that we were aiming at. So across KPIs, we will observe that they perform differently because clearly they have different natures and distributions, but ultimately we will still observe these concept drift trends that I've just shown you. One question that you might ask me is, well, we all know that like if you try to use a model for 4 years, it's going to underperform at some time. So why don't you just retrain periodically? And that's pretty much what operators are used to do. Choose a period of time to cyclically retrain their models. So the next step in our work was trying to understand whether this approach is effective. And we selected a different set of periods to periodically retrain our model and see how much improvement we will observe. And in particular, in this case, we're going to look at still a model to predict download volumes, but we're going to look at the delta of the error between the results that we get for the static model, so the model that gets trained with initial data and never changes, and models that get retrained with 7 days, 30 days, 90 days period, and so on and so forth. So in terms of performance, we actually observed that retraining can be effective. In this particular case, for download volume, we see that the more we retrain, the better results we get. I'm not showing this into this slide, but this is not true for all KPIs. We actually observed that for certain KPIs, performance will degrade if we were retraining too often. But in general, we could say, like, well, for certain features, this works very well. On the other hand, this comes at the cost of having to retrain our models very frequently. If we retrain every 7 days, that means that every 7 days we have to collect data from the network and retrain our models, which can be very costly if done at scale in every metropolitan city in the US or throughout the world. So it's very hard to choose the sweet spot, the trade-off, the perfect trade-off between how frequently we want to retrain and how well our models will perform over time. So to conclude the characterization phase, we were able to demonstrate that concept drift is a universal phenomenon and that just naively retraining is not enough to combat it over time. So can we do better? That's where our solution that we call LEAF, local error approximation of features, comes into play. But before jumping into the solution itself, let me try to give you a sense of the core idea that we use to develop this framework. So here in the plot, I'm showing on the x-axis the distribution of values that download volume had in our dataset throughout the training data that we collected. On the y-axis, we show the error that we obtained for the instances that are used as input to the model that have that specific value for download volume. If we test the model against the training data itself, which obviously is going to give good results, so we expect this plot to look what I'm showing you in the sense that errors are going to be fairly low throughout all the distribution. That is correct. But what happens if we look at a portion of the data set that occurs after concept drift arrived? We're going to observe that for certain portions, and only for certain portions of the data, the performance starts to degrade. That is due to the fact that for these specific regions, the model is undertrained. It's not able and capable of performing correctly as we expected anymore. So if we were capable of using this information to targetedly retrain our model and enhance it in such a way that will compensate its performance, then we will have LEAF as a solution. We call this approach local error approximation because it gives us a perception of where the errors are located given the regions of the distributions of the input data. So LEAF, it's an end-to-end detection, explanation, and mitigation approach to concept drift in the sense that we start from incoming error data from the actual predictions of the model. We use a drift detector to detect whether concept drift is occurring due to the fact that change detection and drift detection in general are a fairly evolved we have fairly evolved solutions in the state of the art. We didn't propose a new solution. We just use Kolmogorov-Smirnov KSWin for detecting whether concept drift was occurring. And we focus on the actual explanation and mitigation of the problem. So we first detect whether drift is occurring, and then we want to explain it. We want to understand what are the reasons for this drift occurring. And this is where we use our local error approximation to first generate values of the regions of error for our features, and second, to generate visual information that the operators can use in the form of a Leo plot and a Leogram to better visualize where the regions of the error are located. So more in detail, what are the steps of the explanation? We first group features in our dataset, in our input, based on their correlations. This is done in order to avoid to have to calculate errors for all the features presented in the dataset. So we group them based on correlation. Second, we rank them using their feature importance, because we want to target the features that impact the model the most. And then we beam values as using the distribution of the values as I've explained before. Finally, we compute the local error approximation and pass that information to the mitigation. In particular, the Lea plot helps explaining the amounts and the regions of where the errors are occurring without needing to access the model itself. So it's working with any model as a black box. And the Leogram that I don't have the time to present in detail helps with the temporal location of these errors. Finally, once we have explained where the errors are occurring, we can pass this information to the mitigator that, using techniques such as forgetting and resampling, can enhance the model and compensate for the occurring drift. So we took our solution and we went back to a similar approach for evaluating the performance of our solution compared to state of the art, and use the delta of the errors. And here I'm showing you these for a number of different KPIs. And in particular, I'm showing the performance of Leaf compared to a naive retraining approach using a 30 days period, and a triggered approach, where triggered is basically using K-swing to detect when concept drift is occurring, but only retraining the model at that point instead of running the mitigation technique that Leaf implements. So with what we observe, if we look at the result for downlink volume, is that Leaf not only improves, even if ever so slightly, compared to the naive retraining approach, but it can also do this by reducing the number of retrains required. This actually applies with different degrees of improvement throughout the vast majority of the KPIs that we studied, with some exception, like, for example, cold drop rate, where we observed that Leaf was performing slightly worse with comparison to the trigger baseline, but Leaf still worked with almost half as many required retrains to improve performance. We also tested whether this approach worked throughout models, and we observed that, similarly to what I discussed for the KPIs, either Leaf outperformed on both metrics, both reduction of errors or number of retrains compared to the other baselines that we studied. And in the case that it will not outperform in terms of reduction of errors, it will still improve largely the number of retrains required to achieve very similar performance results. So while I don't have the time to present here all the results, I invite you to go look at the paper, because we have a large analysis across an even higher number of baselines. We're looking at sensibility of how evolving infrastructure can impact our models, our approach, and also on how morphologies such as more rural or metropolitan areas can impact our solution. So to conclude, I presented you today our characterization study of how concept drift is a universal phenomenon, and presented a solution, Leaf, to tackle it. We are very happy with our results, but we believe that there is still quite a good amount of work to be done to improve how to deploy machine learning models in networks, and to actually sort of encourage the community to participate in this work. We have released a year-long data set that was part of the data set that we use for the study, so that we can collaborate and participate all together in this journey. Thanks a lot. I'm happy to take questions.
Questions or take it?
Thanks very much. I think this is a really interesting work, actually. I have a few questions. So because you're looking at these KPIs in a deployment, do you know how much of the drift actually...
Sorry, can you speak a bit louder? I'm not sure.
Hello? Oh, there we go. So first I wanted to say nice work.
Thank you.
And then I wanted to ask you, so two things. One is whether you looked at, when you see this kind of changes in the data, is it really that the signals have evolved, or did you rule out the fact that actually there might have been configuration changes that trigger those things? In which case, I think a model can't capture that because it's a completely new setting unless you have some super powerful machine learning model. So that's question one. Question two is, does it make sense to use continual learning when you basically kind of learn new knowledge without forgetting the old one?
Sure. Regarding the first question, we treated the problem as a black box, meaning that we did not want to work with the knowledge of what was occurring in the network. And we actually did not have the ground truth to even prove whether that was the case or not. That being said, we were working in the mindset that no matter what, we wanted to improve the model, and definitely in the case the setting changes, retraining will be needed. So hopefully the solution would work anyway. Operators are large entities, so it doesn't mean that they communicate very well within them. Regarding the second question, that's definitely a possible approach. We didn't explore that. It would be interesting in studying which one performs best, and ideally the data set is there to help for that comparison.
Thank you.
Yeah, I'm here, so you can see me. Actually, I had two questions, but the one it was the same question that Paul's had, so I moved directly to the second one. If instead, it's kind of a try to see if it can be applied and kind of a logic. If instead of wanting to follow, okay, the let's say time profile very exact, very with very high accuracy, you wanted to somehow try to predict if the values that you see are going to cause you problems. So you don't want to follow it, but just to see whenever you will have problems. Do you think you can still apply that type of analysis?
In my opinion, yes, for the reason that we are doing a more fine-grained job than what you described, meaning that if we can predict the values, we can potentially predict the problems. That being said, it sounds we will have to dig deeper into the per node base performance to understand how effective it will be, for example, for like problem detection and other sort of anomalies that as you were suggesting. Here we were more looking at the aggregate demands over time.
Yeah, but this could be much less costly. I mean, so maybe some techniques can be used instead of being, yeah, that's what I was thinking. Anyway, I see your point and I agree. Okay, fine, thanks.
Thank you.
So hello, everyone. I'm happy to present our work-dependent misconfiguration in 5G RC. But before I move the page, I want to take a look about the first 4 pictures. They are our students, and all of them cannot count. This is why I'm here. Okay. So today my talk I will focus on actually some surprising result we found at the first place. And then later when we figure out why, and we understand why this problem actually, why this problem happens. And I know most of us in this room do not working on actually like some misconfiguration in cell network. So this is why my talk, I will focus just try to actually make everybody in this room understand this problem, or at least understand the problem better. Okay. So let me tell you actually what happened. The reason I believe it's doable is because even you do not do research in cell network, but everyone used the mobile phone. Everybody use mobile data plan, right? So how you can get the mobile phone works? Very important thing is because we can get the mobile service everywhere. It's because operator deploy cell towers everywhere. So if you really look into actual cell network, your mobile phone actually is served by one cell provided by operator. Like here, we call this one cell is 7 cell, right? Of course, this 7 cell runs on one specific frequency channel. We usually call this one actual frequency, okay, for short. Of course, operator do not deploy only single cell to serve you. They deploy many candidate cell allowed us. For example, today, actually, most operator, I think maybe all the operator have already invested largely in their infrastructure. So you may be already surrounded currently several tens of cells right now. Some places you can even surround by actually hundreds of cells allowed you. So if you really look in the problem, reader access actually fundamentally is a selection problem. It's out of many, for example, NC candidate cell, their operator is going to pick several one serve you done. But how they do selection? This one is called the RC reconversion. So I use a simple example to illustrate background. The basic idea here is originally answered by old cell. Okay, now we're going to switch to new cell. And how to do that? They call this one is handoff, right? But this is a standard procedure used by 3GPP. Okay, it has 4 steps. First one, 7 cell will tell the base station, tell the device, I configure the parameter you should use so that you know how to measure, how to report. And after he received this configuration parameter, he's going to measure. He measured the cells allowed it. For example, he measured a different frequency. Say, what candidates allowed me and what's their signal strength. Let me make a simple example. For example, this example says, okay, the cell tell the device, if you found a cell which is 3 dB stronger than me, you should report. And then the device measured the cell. He found, okay, my new cell is 20 dB stronger than the older one. Of course, based on this configuration, right, he should report. So he report. Once he report, actually, both 7 cell and also candidate cell single strength to the current 7 cell. The current 7 cell realize, yeah, I should switch you to another cell. So very simple, he will tell, oh yeah, you should switch to the new cell. Then we decide to move to new cell, and then 7 cell switch. This is exactly happens actually every moment. Okay, so very simple you can say, right? Pretty straightforward you can say. Here, very important thing is this selection is impacted by configuration. Because the operator this mechanism is already standard, okay? But the policy, the parameter, the threshold, all this one used depends on operator. So actually, I skip the details, just tell you actually 3GPP will define standard. So I'll tell you that this is standard event, A1 to A6, B1 to B2. Basic idea just, oh yeah, if the 7 cell is weaker than sense threshold, or if the candidate cell is stronger than sense threshold, or if the candidate cell is stronger than threshold by some dB, blah, blah, all this one, different rule. And the basic idea is just to help the device to realize, okay, who are stronger candidate cell, so that they can select them. Okay, then it's also pretty straightforward thing about one problem is if it's configured. So if it is disconfigured, then problem will show up. For example, right, you switch selection from cell 1 to cell 2, cell 2 to cell 3, and cell 3 back to cell 1, and keep doing that one. This is called a loop. Or yeah, you choose a cell 1, and then you choose to cell new. But cell new is even prefers worse than cell old. So it means you choose the worst one. Right? This is new in cell network, but it's not new in BGP, right? Think about routing. Or yeah, you find a path. This is a loop. Then packet go here. Or yeah, you find a path. Path is good, but the path is worst path, or it is worse than the best path we can have. Same thing here. So basically, it's one, it hurts stability. Another one, it is hurt reachability. And this one we find actually in the instances actually in 3G network. This is 7 years ago. And we will give some example, show you, for example, the configuration said, if 2 cells are stronger than some threshold, single strength stronger threshold, we're going to switch. So in any place with both cells stronger than this threshold, you will get into loop. Or we showed actually 7 years ago, we still have 2G. They will show you, oh yeah, Thus, you have to switch from 2G to 3G and 3G to 4G. But in some place with 2G and 4G only, you cannot switch from 2G to 4G directly. That's why you are going to lose 4G connection. This is examples we found several years ago. That's not the research I want to present today. Okay. What I want to present today, I want to tell you what's new today. So from 3G, 4G to today's actual 5G, or we can say 4.5G. And the fundamental thing we change is you can say in the 3G, 4G, I have a single 7 cell. But today we have multiple 7 cell. Just show you the right side. And then you can look into the selection problem. It's more like, oh, I'm going to select NS7 cells out of NC cells. We change in 2 things. Number 1, the number of 7 cells increase. Number 2, number of candidates greatly increase. This is easy to understand. So we increase number of 7 cells is because we indeed need to provide high speed, right? So we use actually dual connectivity. It means we can use 4G and 5G together server you. And then we use carrier aggregation. It means we use multiple cell server you. And a very simple example will show you at the very beginning, we have a carrier aggregation. We use 2 cells. And now release 15 can allow us to use up to 16 cells. Okay, for non-candidate it's easy to understand. Number 1, the operator deploy more and more cells because they want to have dense deployment so that they can improve the capacity. Second one, we use much wider spectrum, right? And today, actually, in United States, I don't know which one use Europe, but the basic idea is, we assign, right, more and more actual licensed band so the operator can use wide spectrum to serve these devices. What do you mean that? This one means if the NS increase, NC also increase, it means that when they scale up, it means we have hyper capacity. But it also means much, much, much better actually the complexity. The reason is because in the past, if we have single 7 cell, we just do actually like some single action procedure. But if we have multiple cell, we actually multiple 7 cell, it means maybe we are run multiple round. So it's within the 7 cell set, we are going to have a configuration dependency among different round. For example, my previous round configuration may hurt my conflict with my configuration actually next round, so that they will hurt performance and in a way you never expect. Before I tell you actually the thing, I just give you a quick actual background about the cell network. For example, I use this kind of 4 7 cell show you they actually use 2 technology, right? First one is we have 4G and 5G. So blue one means 4G cell, green one shows 5G cell, and we use technology called dual connectivity. And then we say, for example, we say 4G cell is a master cell group and the 5G is a secondary cells group, and both actually used to 7 device. And within the same group, they can divide into primary cell and the secondary cell. So it means that this is how they actually say we use multiple cell to serve a device. Okay, but no matter how many cells used, we call this one single cell set. So it's a set of multiple cells. Now, the key here is I want to highlight the P cell. It's because this is the only one cell is going to respond for RC control. This is for the function in control plane. Because all the cells are used to provide data, to transfer data in the user plane, data plane. But the actual control plane, we mainly count on P cell. So I will use P cell to show you how it happens. So all the example will show, originally I have 2 cells use 4G. Now I'm going to use new selection and switch to a new cell set with 4G cell and also 5G cell. We do similar thing. First round 4 step, configuration measurement, reporting, and decision. Good. You switch from PCL1 to PCL2 because actually this PCL is better, right? This 4G cell is better. That's why I switch. And then he prefer 1, 2, 3, 1, 2, 3 until the set conversion. They run multiple rounds because they may add some cells at one step, but they may not add all the secondary cell or all other secondary cells at the same place. So it means he may run multiple rounds. This is a real example. For example, we run 3 rounds. First rounds, we get the P cell. Second rounds, we get a secondary cell in 4G. And the third round, we get a secondary cell in 5G. And that means it will be definitely wrong. But unfortunately, in the real operation, we found interdependency in multiple round configuration. So I try to use a real world example with AT&T to help you to understand the problem. There's something is maybe difficult to understand. For example, we have a number and forget this one. This is not important. Forget about frequency. You should know actually this is just represent one cell, okay? We also show you SRP value is not important. The real important thing is their comparison. We are going to show you actually a loop. This loop will happen every 4 seconds. So basic idea this way. Originally, I have one cell and 4G master cell. Then I measure 5G frequency because I need to ask a rule. Say, if 5G single strength is a higher than threshold, here is minus 115 dB. You should report a 5G cell to me, okay? So he measured a 5G cell. And he, of course, 5G cell is stronger than this threshold. So he report that. When he report this one, he is going, we can say 5G1, it means he added this cell into his 7th cell. But once he added this 5G cell into his 7th cell, he changes configuration. Pay attention to this one. The key here is we changing the configuration is we actually, doesn't work. You can say the strike line, okay? So it's basically thing is my original threshold rules removed. Instead, it's replaced by a new one. We'll say A2 event. Basic idea say if your single strength is weaker than that threshold, I'm going to move you. Check this value, right? Okay, then I can show you this is the report and new cells. But you know, SRP value, this one, pretty dynamic. So a few seconds later, he will measure a new one will show my SRP value is smaller than threshold you want. So I report my measurement to the cell. Then I say, oh, 5G cell is not strong enough. We should remove that. Then he go back to remove the cell. Once he go back to remove the cell, he go back to the original one. Okay, we should measure 5G cell if the single strength is larger than minus 1115 dB. Okay, and then after we add this in, and then we'll check, okay, if your single strength is below than 95 dB, minus 95 dB. Now you can imagine what happened, right? So in any place with 5G cell single strength is between these two thresholds, he get into the loop. This is exactly happened actually in our experiment. We more than this one, more than 5 minutes. But if you want more, it's very easy to say the loop actually repeats itself every 4 or 5 seconds. Period. That's the major piece of the presentation. Just show you understand 5G actually of dependent misconfiguration actually in today's 5G. This is mainly because the number of 7 cells larger. It means that when we scale up our resource used to support 5G, unfortunately, complexity also increase and the misconfiguration happens. And we indeed find actually in this study, we indeed find actually new dependent misconfiguration, which is very, very different from our previous finding in 3G, 4G, and the other configuration. And we do have state machine show you actually the approach, how we do that. I may skip these details, but I will briefly tell you how it works. Because I said today's focus is just help you understand this problem, which is more important, how we solve this problem. So just to show you actually given this one, given this new dependent misconfiguration, we have the same problem. We still have a loop. It means we are hurt in stability. We also have worst handoff. It means we also hurt reachability, right? We also test with actually, just test with actually 4 operator data set in the past 4 years. So basically we have identified actually more than 600 actual instances. This is all are real instance. You can say this misconfiguration happened in operator. Of course, they are not a common case. If it's normal common case, then we will not have network today, right? But anyway, we still can say actually accept. We can observe this happens. And more important, when this issue happens, the performance is really, really bad and it sucks. And all our data set and the source code already released. And I just want to give you, so this is our major contribution, but I still want to give you actually a view about actually the problem. In this example, we show you, for example, in this example, we show you with the loop, the performance we get is 5 Mbps. The maximum speed, all the speed is below than 15 Mbps. But I want to show you if there's no loop, if we use 4G and 5G together, if we disable the loop, we can get 400 Mbps. That means we lose 2 orders of the magnitude of the data speed, 99% throughput drop. That's not a corner case. This is commonly observed actually when the loop happens. It's not hard to understand, right, this one. And I want to highlight why this is important thing. Just this is the misconfiguration. So if you check, when 5G is not used, we use configuration B1 event set 1 threshold. But when 5G cell is used, I change configuration in another way, right? And these two configurations actually conflict. So that this interdependency misconfigured will lead to the loop. How we detect this one? This is a major contribution we have, but unfortunately, due to time limit, I will quickly, I may just briefly give you some idea, but for those, maybe very few people who are interested in this topic, I will encourage you to read the paper because there's a lot of actually the dirty details there and here. I'll give you a high level idea. High level is pretty straightforward. The basic thing is we build a state machine. So you can say, oh, I have a cell set and I have a configuration. Then given the configuration, I can figure out actually what will be the decision I'm going to make. And once I have this, I can send, given the configuration, I can manage actually what kind of reporting I'm going to receive. Because reporting, what to report result depends on how you configure the parameter. And given this reporting, I'm going to tell you which cells I'm going to select it. So more this one, I can build a state machine. This is called a naive state machine, very similar to FSM. But all this data is configuration. Then I can calculate variation. For example, oh, you are violated press loop, or you can create actually the worst handoff, which means the worst reachability. Then we can count the same. This is our high-level idea. The only problem with this high-level idea is state exposure. Which I show you, give you a simple example. The configuration is not a, it have many configuration entries. For example, here we show you the one. I just highlight the important one. And if we add a new 5G cell, we switch to another one, but other part remains unchanged. If we check other cell sets, we move back. But if we check, we have many cell sets. So it means it's not you are served by single cell set. Actually, you can maybe served by multiple, 10 or 7 or even more. Actually, kind of actually cell set. But if we check a configuration, a lot of parts are not important, but only these two are major one. So it's basically if we do use naive approach, we're going to have a state exposure. Our idea is pretty simple because we do a delta state machine. So basic idea is given any configuration state, we divide it into two parts. One is the state. Yeah, we have a state is more like a given two configuration, we get the delta. This one is depends on actually the parameter. We also get the intersection, this means the common part. And the most common part are independent about the change. So we can use the actual delta state machine and then the figure. Then we can say, can simplify all the state machine, then you can realize, oh, this is pretty simple. We can come up with these two major rules, then that. Of course, I will skip a lot of the details after this one. After we come with DSM, we have to do misconfiguration analysis. Basic idea is we have a state, so we need to look into in-state transition. We also look into within single state, we have multiple configuration parameter. We also check their configuration. So for those interesting, I will encourage you to read our paper. I skip them here, okay? But give you some exciting news or not exciting. I want to show you why our paper get in is because we really show this is a real problem, okay, in operator. So this is the data set. And I want to show you the problem we identify. We identify, if we do state transition, we identify two types of problem. This problem will lead to both issues. One is loop. Another one is your some important second cell will be missed, so that your performance is worse. Okay. For the intrastate, we actually show you can have some second cell removed, but they should not be removed. You can have some handoff, they should not go wrong, but unfortunately they go wrong. Or you have handoff, they should not fail, but unfortunately they fail. So we check out this is the incident number. You can know the D1, the D2 will be the major issue. So it means actually this first category is the major issue. And I give you quite a clue about this one, just a real example. This is 5G cell will show if we have A2 event and B1 event, if configuration parameter go wrong, they will cause the loop. We also have A2 and A1 event if we configure some parameter. So this parameter will lead to some loop. And this one, very similar to the example I explained actually in this presentation, okay? So this is actually the real number we just studied. This operator, actually US one is AT&T, okay? The basic thing here is we just show you how many PCLs we have this problem and how many frequency we had this problem, what the threshold we have. We realize actually this happens almost all the frequency used by actually AT&T, okay? We also check actually for another event, we can realize these issues happened all three operators and this is the parameter they have. And the performance issue, as I showed you before, they can lose 99%. It means 2 order of the throughput loss. This is the very bad. And the signal overhead at least increased by 1 order of magnitude. Of course, he also will lead to disruption. And then this is some example. I just want to skip this one. The basic idea just shows actually some second cell will be missed. It means they supposed should use actual 5G cell. Unfortunately, they stay with 4G cell without use 5G cell. This is why their throughput is much lower. And we have both cases. Some 5G cells missed, some 4G cell missed. And both happened in all the operator except China, because China we do not observe data with 5G. So we in the two operator US 1 and US 3, we observe this issue. I skip this one. Let me give you a quick summary. This is some result. Just to show you, this is the detail, tedious detail, show you actually the problem happens and they really hurt performance. As long as you understand actually how misconfiguration happens, it should not be too hard for us to understand the performance will get hurt, right? So let me give you the conclusion. This is the work we done. So number one thing, we show you a new misconfiguration in 5G, mainly because our number of 7 cells scales up. And with this one is new for it because this is dependent misconfiguration. It's because when we have more cells and our configuration changes with the 7 cells we use. And it hurt the performance in both with the loop and also worse reachability, right? And validated in our data set. And we release all this code so you can likely can say code, data set, everything can be reproduced. I think that's all for my today presentation. I'm happy to take your questions.
Thank you very much, Chunyi, for the presentation. Questions?
Thank you for the very interesting talk. It seems like this study is based on NSA. So does this kind of misconfigurations can still be observed in modern SA networks? That's my first question.
Well, what
in SA networks in 5G SA standalone? So that's my first question.
So this is a good question. So let me explain something. So if we do computer science, we know any system we have a mechanism and also policy. So standard only can define the mechanism. It means, for example, I show you the RC, how we select the cells. We have a configuration step and then measurement and then reporting and then decision. All this one are specified by standard. However, operator standard will never tell you which parameter you should use. This one is done by vendor. For example, Nokia, Huawei, by all these companies. And then when they ship their document to the operator will also change based on their deployment. So it means this parameter can be configured. And this configured parameter, you try to implement the policy specific by operator. Make sense for you? So right now we can say the thing here is because this parameter set by operator. And when they work together, they actually lead to the issue. But every parameter used for single cell makes sense. And of course, there's many reasons for operator to configure parameters. For example, I say my threshold should be 3 dB than yours, right? And then you can say, if I get some cells, I will think about it. I should consider how to remove you because when I do not have 5G cell, I need to think about how you set the new threshold so that I can get 5G cell. But once I have 5G cell, I need to think about actually how should I remove 5G cell? Because if the 5G cell is not strong enough, I should remove that. Make sense? So all this kind of parameter at configuration policy make sense. But unfortunately, based on the parameter they use today, when they work together, this lead to the misconfiguration.
Understood. Yeah, thank you very much.
So hello, my name is Dogu Kim, and I'm going to present the FlexCP, a scalable multipath TCP proxy for cellular networks. So multipath TCP or MPTCP has a great potential to improve the performance and the resilience. So you can see the overview of the MPTCP connection, and the client and the server can establish multiple TCP subflows under the one MPTCP connection. So in this case, the MPTCP connection manages two kinds of the sequence number, data level and the subflow level. So while the data level sequence represent the sequence number for the whole connection, each underlying subflow also manages their own subflow sequence we call the SSN. And every data has their own mapping between this data level and the subflow level sequence like this. And then this is the data sequence mapping. So this MPTSP is now ready for the real-world distribution, as the large of the operating system, including the Apple iOS and the Linux kernels, now supports the MPTSP protocol. However, the reality is that the MPTSP is not widely adopted yet by end-to-end connection. So one analysis says that less than the 20 kilo servers in the entire internet can cover the MPTSP capable package, and the majority of the servers still use the normal TCP without supporting the MPTCP. So it makes the MPTCP proxy is required. So right figure shows the MPTCP proxy, and the proxy terminates the MPTCP connection with the client, and it relays to the server to the ordinary TCP connection. And the cellular network community has standardized this MPTCP proxy as the ATSSS for the 5G network. And some internet service provider have already adopted this MPTCP proxy for their own network. Unfortunately, currently the MPTCP proxy has some suboptimal performance. So the below figure compares the Nginx proxy and the server, which use the MPTCP and the TCP on the 400 gigabit per second link. So left to one is regarding the MPTCP proxy and the just normal TCP proxy. And the right to one shows the end-to-end scenario without the proxy. And in this case, the performance is measured at the server. Now we can see the two interesting points. First of all, when it comes to the end-to-end scenario, the using MPTCP get lower performance compared to the TCP. And we found it that this is because that the current Linux kernel has not fully optimized the MPTCP protocol yet. But anyway, the MPTCP also scales up to the 300 gigabits per second in this case. However, the second thing is that when we compare the proxy and the end-to-end, we can see that the MPTCP proxying incurs a huge overhead compared to the end-to-end for up to the 3.4 times. And it is notable that not only MPTCP proxy, just using TCP proxy also get a huge overhead and degraded compared to the end-to-end. So why using this proxy becomes bad? And this is because that there are two physical connections between the client and the server. So let me say that the server sends the packet to the proxy like this, and then the proxy terminates this connection by the storing at the receive buffer, and then it reassembles the flow to the client side, and it sends like this. And you can see that the orange packets are out of order packet, and it is still blocked at the proxy. And in this process, the proxy must manage the multi-access connections. It means that as the proxy participates at the endpoint between the client and proxy, and then the proxy and the server. So proxy should manage the connection, which including the ensuring the reliable data transfer and the congestion control, flow control, and so on. And lots of the CPU cycles are rated on this connection management. And proxy can be easily get overloaded. So now we want to suggest our FlexCP, a flexible connection proxying through L3 switching. So in this case, there are only one physical connection between the client and the server. And the proxy just run in the middle of the connection without the buffering or blocking. And then everything, including the congestion control or flow control, are done by the client and the server. So proxy just do following three things. So in this case, when the server sends the packet, then the proxy just parse the packet header, and then it translated, including the for tuple, and also inserting the MPTCP option, and then checksum, and then it forwards to the other side. And it is the work just done in the L3 switch like. And in this packet level translation and forwarding, proxy can benefit from the existing DIG offloads. So here are our design rationales for FlexCP. So we designed our work with one observation that today's Wi-Fi and cellular networks have high enough bandwidth. So if there are enough bandwidth underlying the link, then actually it might be more important that preventing proxy from being a bottleneck. And also, there are no need for bandwidth aggregation for a single connection if there are enough bandwidth achieved. So it means that it is enough for mapping one TCP connection to the one subflow, not using the whole subflow simultaneously, because using one subflow can get high enough bandwidth. So the FlexCP So the FlexCP maps the one TCP to the one subflow, so that when it comes to the many concurrent connections, then some of the MPTCP connection will be go to the subflow 1, and some will be go to the subflow 2, and some will go to the other, and so on. And this path scheduling is done on the flow level rather than the packet level. Of course, it is important to modify the subflow to the different paths if the current one becomes bad, like connection failure or a link failure or link congestion and so on. And in this path scheduling, our FlexCP supports lots of the ATSSS modes, including active standby, load balancing, and smallest delay. So now I will explain how the FlexCP does translate the packet and forward to others. So basically, all packets should be forwarded immediately without buffering or blocking at the proxy. And then it should be applied on the control packets. So we adopt the 0 RTT TCP convert at the handshake level. So you can see that the client sends the SYN packet, and it is directly translated to the normal TCP SYN. And then the subsequent packets are translated same. And well, important thing is that the clients also send the second SYN packet with the MP join, and this is not forwarded to the server because server side connection is already established when first subflow. So in this case, proxy just reply the CNAM plus MP join packet, and then the clients also reply with the ECK packet, and the connection is established. And when it comes to the teardown level, there are two kinds of the FIN packet in the MPTCP. So subflow level and the MPTCP level. And MPTCP level is called to the data FIN packet, and then the clients send this data FIN to the proxy, and then it is translated to the normal TCP FIN and vice versa. And of course, the client's FIN packet for subflows are not forwarded to the server because the server-side connection is already closed. So in this case, proxy just reply the ECK packet to the client back. So this was what the FlexCP does for the control packet, and now I will explain the data packet. And the most important thing in this process is the sequence number translation. So there are two kinds of the sequence translation. And first thing is the TCP SN to the DSN. And it is really simple because the difference between the TCP SN and the DSN is always constant. So the translation is done by just adding the offset between two values. And then it does the second translation, which is translated to the SSN, subflow sequence number. And it is assigned according to the path scheduling. That I means that the proxy, you can see that the first packet from the server is translated and forwarded to the first subflow 1, and the second packet is go to the subflow 2, and then the proxy stores this information in the data sequence mapping, and then it assigns the subflow sequence number. And of course, there are two directions, TCP to MPTCP direction and MPTCP to TCP directions, and FlexCP should maintain both DSM information. However, there are challenges on this sequence number translation that it might be a really huge overhead. So let me say some example. So in MPTCP protocol, the retransmission packet should send to the exactly same subflow flow ID with the exactly same the sequence number. So let me say the server have retransmit the packet with sequence number Z1 to the Z3. Then the proxy should find the which DSM entry contains that sequence number, and then it found after it found it, it translates to the corresponding DSN and SSN. Of course, in this case, the packet is split because these two entry has the different subflow ID. So it incurs the search by the TCP SN. And another example is the translating selective ACK. So in this time, the clients send the selective ACK packet to the proxy, which ACK number is the X2 to the X3. And please note that the SEC number is just on the subflow level, not the data level. So in this time, proxy should search which node contains the SSN X2 to the X3. And then after the find, it translates to the corresponding TCP SN Z3 to Z4. So all of this might be really huge overhead because in naive implementation, it will incur the linear search for bidirectional mapping, DSN to SSN and SSN to DSN. So we mitigate this overhead to use the D3. It is the scalable sequence number translation. And basically, our D3 is consisted of the red-black tree, which node key is the range of the DSN. So let me say that the server have retransmit the packet with sequence number 950. Then we just search this DSN by scanning the red-black tree, and then yeah, it hits. And then we see the contents of the nodes, and then it has the DSM information, so we can retransmit to the corresponding sequence ID, sequence number with the sequence subflow ID. So then I will show another example. When the client sends the SEC packet with the SEC number 300, then in this time, proxy also need to find which node contains the subflow sequence number. But you see that this red-black tree only shows the DSN, not the SSN. So in this time, we look at the contents of each node. And when we see the root node, then we found that it contains the subflow ID 1 with the SSN 200. So now the proxy knows that we should go to the right side. And when we go right, and right node contains the subflow sequence number 500, then we need to go left. And so it go left, and then go left again, and then it hits. Now this node contains the correct subflow sequence number and subflow ID. So and we translate the correct data sequence number 500. Actually, this is really a simple example, and I skipped lots of details on this presentation, but I think it will be too complex to explain all of this. So please refer our paper for getting more detail on D3 structure. So now I will explain another challenge that using RSS cannot support the flow to core affinity in terms of the MPTCP. So let me say that the clients have established the subflow 1 with the proxy, then the NIC in the proxy have distributed it to the core 1 via the RSS hash values. However, when it comes to the subflow 2, as the hash value as the protocol of the subflow 1 and 2 would be different, so the RSS hash also might be different. So in this case, NIC distribute to another core, and it occurs, it incurs the resource contention. So to resolve the resource contention, we should maintain the mutex locks to access the connection table. And actually, the Linux currently use the lock contention lock for the MPTCP, but we found it incurs serious overhead. So what we suggest is to exploit the smart NIC to augment the RSS. So in this case, we can configure the system as the instead of the ordinary NIC, the smart NIC receives all the MPTCP packets, and it magically knows that the subflow 1 and 2 would go to the same flow with using their own processing power, including ARM core and memory. And then the server side TCP package go directly to the CPU, and it does not undergo the SmartNIC using the normal RSS. And it is valid because server-side TCP only has the one flow. So then, how the SmartNIC magically know these two subflows should go to the same core? And I will explain the detail on this. So first of all, the SmartNIC maintains two kinds of the table: flow to core table and the token to core table. And then when the client sends the first SYN packet, and then SmartNIC tries to find this packet information to the table. And first these two tables are empty, so it is misses. And if there are two misses, then the SmartNIC send to the host with using just RSS. And let me say it is distributed to the core 2. Then now host 2 receives the packet, and then it tells the SmartNIC that this packet was be distributed to the core 2. And then SmartNIC received the message and it stores the information to the flow to core table. And also, hosts now know that not only this subflow 1, this MPTHP connection itself also should be forwarded to the core 2. So the host send additional message to show that information, and it is stored in the token to core table. And then the host core will forward the same packet to the server, and the subsequent package will just go to the host directly. And then the host client will send the ACK packet with the application data. And for this, SmartNIC also try to find this flow information, and actually it is hit at the flow to core table. So SmartNIC now knows that this flow should be go to the core 2, and then it actually send to the core 2. And this is the second phase. The client now sends another SYN packet via the subflow 2 with the MP join packet. In this case, SmartNIC fails to find the flow to core table, but in terms of the token to core table, it hits because the client's packet contains the token 1 value, and SmartNIC parses it and used to find the token to core table. So using that table, the SmartNIC send to the host core 2. And then SmartNIC now knows that this packet should be go to the core 2, so it store the information of the subflow to the flow to core table 2. And then the host core will reply the CNAM packet, and then the client will send the ACK packet with the application data. And this is also hit at the flow to core table, so it is sent to the correct core number. Yeah, and this was the design and the implementation of our FlexCP. And now I'm going to explain the evaluation. So here are the setup of Proxy, and we use the two Bluefield 2 SmartNIC, which have the dual port 100 gigabit per second links. And we use the two backend servers, which runs the Nginx servers, and we use the 4 client machines to generate the HTTP request using the H2 load tools. And this is the result of our throughput improvement evaluation. So left 3 ones are the baseline, and the right one, blue one, is our FlexCP. And you can see that our FlexCP largely outperformed the other baselines up to the 6.3 times. But however, actually, this might be not the apple-to-apple comparison, because when we evaluate the baseline, we only use the host CPU without the SmartNIC. But in terms of our FlexCP, we use the SmartNIC. So actually, the performance might be due to the host CPU plus the NIC cores. So to get the balance between two, we additionally do the same evaluation, but running the Nginx and the HA proxy on the Bluefield SmartNIC. So this is the performance of the SmartNIC, and we can see that the SmartNIC have some weak processing power, so it does not perform no more than the 10 gigabits per second. So I think this is the typo, not 7.2. So it shows that our FlexCP our FlexCP is not due to the SmartNIC processing power, but it is thanks to our FlexCP design. And we also compared our FlexCP, which used the flow to core affinity and which does not use the flow to core affinity. And we implement one more version of FlexCP that used the shared memory with the mutex lock. And we found that using the flow to core affinity with SmartNIC can boost up about 1.4 times more throughput. And now I will show the FlexCP performance under the dynamic link status. So the first for the first 5 times, 0 times to 5 times, there are only one subflows available, and path 2 is not available. And so therefore, in this time, the path 1 is saturated to the 100 gigabits per second. And after the 5 times, we enable the path 2, and then the our FlexCP now starts to for the connection to the another subflow 2. And so therefore, the throughput is aggregated to the near the 200 gigabits per second. And then at the 10 seconds, we make the path 2 becomes really poor by adding the high latency. So in this time, FlexCP detects that the path 2 becomes really poor, and it turns back to the path 1. So the most of the connection would goes to the path 1 again. And finally, this is the latency improvement evaluation. And we can see that the blue one is the FlexCP. Our work is the really outperforms than the existing baselines, which is the right side ones. And then even it is almost as good as the end-to-end MPTHP connection, which is the left of the FlexCP. So this is our conclusion of the FlexCP. So existing MPTHP proxy suffers from the high overhead. And this is due to there are 2 physical connections, so it incurs the flow reassembly in the proxy, and also it should manage the both MPTHP connection and the TCP connection. And our FlexCP avoids them by using a single connection abstraction. And also it incurs some challenges, but we addressed it by exploiting D3 and then leveraging the SmartNIC. And as a result, it improves the performance of the existing proxies. So it achieves the larger throughput as well as the low latency. Thank you for listening to my presentation, and I'm happy to await your question.
Thank you. So just a clarification on the experimental methodology. So did each, I wasn't quite sure what the configuration, but each server had 2 NICs in it?
Yeah, so I for the evaluation, so I used the one proxy under the 2 Bluefield SmartNICs.
I'm calling it a question. How you managed to get, if the communications was between a pair of Bluefield NICs, then how did you manage to get over 200 gig? Because they've only got 2 100 gig interfaces. It's about slide 19, if you want.
So
each NIC. Yeah, so the question is, did the host contain 2 NICs?
Yeah.
The proxy.
Yeah, that's the 2 NICs. Yeah. And each NIC you have multiple
Are you counting the in and the out? Are you counting double counting bytes? So you're counting them going into the NIC and going out of the NIC. Then how can you get more than 200 gig?
You have 2 NICs. Each NIC,
but it's a proxy. So effectively 200 gig goes in one side and flows out the other.
Receiving out. Receiving and sending, right?
Yeah.
It's
so you're counting the receiving, and then you're counting the delay.
We only count the server states that we have enough server states.
I think you're touching on function. I didn't understand your experimental configuration.
Yeah, nothing in diagram. So
I'll look at the paper, but yeah, if you mean that cheated in the way you did the math,
No.
or your or the configuration is really mystery.
Servers can be
So you can't do 400 gig if it's
it can be 600 gigabytes second, and then
Next round after the
Yes,
break. Other questions?
Thank you for that nice system work and the new way of doing MPTCP proxies. I have one question on slide 23. Can you go back to
23.
slide 23? Yeah.
Is it right?
So here you show that so you can aggregate two paths when they have exactly the same delay, and then
Yes.
when the delay increases a lot, you only have one path. But what happens when the second path has a slightly higher delay? So you have, I guess, for the first pass, you have that's the direct pass. The second pass, when you create it, you have a direct pass as well. So you do load balancing between the two, and then at 10 seconds, you heavily increase the latency. So let's say you add the 100 millisecond.
Yes.
But what happens if you add only 1 millisecond to make the pass a bit worse, but not completely bad? Because that's a possible scenario. So you have just a rerouting in the network. So you have your path changes a bit.
So are you talking about the time 10? 10
Yeah,
10
at time
seconds?
10. So instead of having a very high latency, you just
right.
slightly increase the latency.
So in my that's right. The proxy needs some time to detect the high latency of the path 2, and we set it as the 0.1 seconds. So actually, the performance of the path 2 drops immediately, but the proxy might not be detect for these 0.1 seconds. So I think you can see that this performance of the path 1, which is orange one, is it tries to decrease the dramatically, but after the 0.1 seconds or some more other offset, then I think that the proxy detects it and is successfully modify their main subflow to path 1. So after that, the path 1 subflow, path 1 throughput now recovers to the saturated.
So I have another answer. So I think it depends on the policy. So you can set up the policy on when you switch to a new the link. So if it's a 1 millisecond inflation, maybe you don't care. So this policy itself can be it's separated from the implementation itself.
Yeah, but I prefer to have the answer of the presenter. So you can configure policies in FlexCP to specify what to do, because one of the possible limitation of FlexCP is that it's quite difficult to handle aggregation, but you show that there is a possibility where it works. So it's difficult to handle aggregation because you don't maintain two different congestion control schemes per pass. So you have only one global congestion control scheme, and there is no congestion control at the level of the FlexCP software because you only do translation of the header. So have you tried different scenarios to explore where this end-to-end congestion control scheme works still, although you have no congestion control on the proxy? I suggest that we take it offline then.
Yes.
Okay.